Okay, so today we're going to talk about exponential growth and exponential decay. So we talk a lot about linear functions, and when we talk about linear functions, they have a constant rate of change. That's why they increase linearly. Okay, they go up in a straight line. Okay. Today we're going to talk about exponential functions. An exponential function increase by a common ratio. Okay, these increase exponentially. So these are going to not be a straight line. These are going to be more of a curve-like feature to kind of get them going. Okay? Exponential functions, they can be modified by exponential growth or exponential decay. Okay, growth meaning they're going up, whereas decay means they are going down. Alright, so we consider the following table, and what we need to find is we can find the difference between those two. Okay, so 1593 minus 1500, that'd be 1593. Okay, this one will be 99. Okay, that'll be 105 for those two. These two, 1908 minus 1797, would be 1111. And then this one would be 118. Okay, it says, what is the starting amount of money in our fund? And our starting amount would be $1,500. It's the point when x is 0 all the way up here at the top. Okay, that's our initial value. Okay, the common ratio, to do the common ratio, we do the change divided by the original. So what I mean by that change, that's the very first subtraction right here that we did. Okay, in this case it's 93. So it's 93 divided by the original. The original amount means the initial amount, which is 1,500. That's what we just answered in the previous question. So we do 93 divided by 1,500. This gives me 0.062. But we need to write it as a percentage. So we write it as, remember, 2 decimal places moving to the right. So it's 6.2%. And because it's a growth that's increasing every time, we say 6.2% increase. 6.2% increase. Okay, let's do another example. Here we have a fish pond. Now the population, and they're decaying over time. So we're going to do 14,204, or 13,494 minus 14,204. That gives me negative 710. Okay, then we're going to do it 819 minus 13,494. Gives me negative 675. We go 12,178 minus 12,819. Gives me negative 641. And then we're going to do 11,569 minus 12,178. Gives me negative 609. Okay, it says which of the following is the initial beginning population? Our beginning population was 14,204 fish. Okay, and it says what is the ratio? Again, it's the change divided by the original. There, the initial. Our change on the very first one, we don't need to put negative, so it's just the number, which is 710, over the initial, which was 14,204. Let's divide that out. Give me 0.05. And remember, to change it to a percentage, so our rate was a 5%, and because it's going down, a 5% decrease. 5% decrease. Okay, we can use functions, a times b of x, to write equations and model these examples of exponential growth and exponential decay. The letter a is our initial amount, and it's the amount we initially start with. Okay, and we have exponential growth. That b variable is equal to 1 plus the rate of change. Okay, that rate of change has to be written in a decimal form. And again, I will do examples of these in a second, so just stay with me for right now. Okay, exponential decay, that value of b is 1 minus our rate of change. And again, that has to be in decimal form. Okay, so let's do some examples. Here it says, back to the original bond fund that we were given. It says, write an equation that represents the exponential growth of the bond function. So again, it's y equals a times b to the x power. Okay, so it's y equals the initial amount. The initial amount here is $1,500, so it's 1,500 times our b. Since it's exponential growth, okay, because we know that because it says increase here. Since it's exponential growth, it's going to be 1 plus the rate. Our rate here is 6.2%, but we need to convert it back to a decimal, so it's going to be 0.062 to the x power. So our function would be y equals 1,500 times 1.062 to the x. Okay, so here is our function right there. Okay, it says how much money would be in the account at the end of 10 years. So it says y equals 1,500 times 1.062. X is now going to be represented by 10 because we're doing 10 years. So what you do in your calculator, you need your calculator for this, you do 1.062, and then there's going to be a button like x to the y or y to the x on your calculator. If you need help finding that button, let me know. Okay, hit that button, and then click 10, hit equals, and then keep that number there, and just hit times your initial, which in this case is 1,500, and we get y equals 2737.39. We got to round up because we're dealing with dollars. Okay, you got to go 2 decimal places because you're dealing with dollars. And it says the same thing, and it says y equals 1,500. This time, our x is going to be 20 because it's asking us for 20 years. So same thing, our calculator, do 1.062, that xy button, 20 equals, then times your initial of 1,500, and it gets y equals 4,995.53 cents. Okay, that's going to ask us to sketch a graph. So on this side, I'm going to go by 500s. And this is going to be my money in dollars. Okay, you should always label your axis, money in dollars. Down the bottom here, I'm going to go up by 2s. Okay, and this is time in years. Time in years. And if you go back to our initial function here, there's a bunch of points here, okay, a bunch of points. These are all order pairs to that graph, so we can go ahead and use this picture here, this chart, to graph our points, okay. So it says the first point was 0, 1,500, so that's my initial, that's going to go right here. Second point was 1, 1,593, so just above 1,500. Something like right there. That's 2, 1,692, so just a little bit higher. 3, 1,797, so it's going to get even a little bit higher. 4, 1,908, so even a little bit higher, almost right on 2,000. 5, 2,026, so again, almost right on it. Okay, and then we also have these points up here, which is 10, 27, 37. And then you have 20, which is 20, 49.95. Almost up there. Okay, so you can see here, it's going to start to curve up to something like that. So there's my exponential growth function. So let's do another one. Okay, again, we're writing the function, so it's y equals a times b to the x. Remember, a is our initial, so our initial for the population was 14,204, and it's times. Since it's decreasing, we're doing an exponential decay, so it's going to be 1 minus our rate of 5%. So 5%, 1, 2, will be 0.05 to the x power. Okay, so our function will be y equals 14,204 times 0.95 to the x. Okay, so there's my initial thing. Again, it's going to ask me for 10 years, so y equals 14,204 times 0.95 to the 10th power. So we know x is 10 because we're looking for 10 years. So again, in my calculator, I'm going to do 0.95. That x to the y button, or y to the x, 10 equals, and we're going to multiply that to our initial, which is 14,204, and it's going to give me 8504. And I need to stop there. I'm not going to round that decimal up or down in any way, because we're dealing with populations. You can't have half of a fish, so that's where we're going to stop there. And then that's again for 20 years, so y equals 14,204 times that 0.95, and this time it's going to be to the 20th power. Okay, so 0.95, that yx button, 20 equals, and then we're going to multiply that to our initial 14,204. And we're going to get y equals 5091, and again, we're not going to round that up or down, we're going to leave it there, because that's what we're going to do. Okay? You're going to have half of a fish. So here, I'm going to go on my 2's. Okay, we're going to say this is population. Okay, in the thousands. Okay, population in the thousands, and then again, I'm going to do this by 2's. Okay, and this is going to be time in my years. Okay, and just like that other problem, and we had a chart here for this problem as well, right there. Okay, so we can graph all of those points. Okay, so I'm going to take a picture of it so that I know where I'm at. Okay, so we're going to graph all of these points. So the first point is going to be 0.14204. 0.14, so it's going to be somewhere probably about right there. Then you got 113,494, somewhere about right there, I guess. 212,18, somewhere about there. 12,17 for 3, so it's close to 12,000, very, very close. 11. Right about there, and then we're going to have at 10 it was 85, 10 was 85, so somewhere about there, and again these are just rough sketches, not going to be very accurate, and then at 20 it was 5,091, so somewhere about there, and as you can kind of see, there is a slight curve to them. It's rough. There's a slight curve to them. Alright, last one. Rapid population Central Park was 150 in the year 2000. The population is increasing by 11% each year. Okay, so it's a finite variable. So we're going to say x. Remember, our y equals a times b to the x. X is going to be the number of years since that study started, which was 2000. So since 2000. Y is going to be my rabbit population. Okay, so Y is that rabbit population that we are trying to find. Okay, it says a reasonable domain. Okay, domain is the axis, so we know it's x. Okay, we know x has to be greater than or equal to our initial year of 0. Okay, it's going to be year 0 because we've identified that x is since 2000, so we're always start with 0 there. It says write an exponential function, so y equals a times b to the x. Remember, a is our initial, and they said that our initial population was 150 rabbits. Okay, so it's going to be 150 times. Okay, we need to identify its growth. It is growth. It's increasing by 11%. Okay, so it's 1 plus since it's growth. If it was decay, then it would be 1 minus. Okay, 11%. is the same as 0.11 to the x. Okay, so our function is y equals 150 times 1.11 to the x power. Okay, and it says, what will the rapid population be in the year 2025? Okay, 2025 is 25 years since 2000, so that means x is 25. And again, and this is where our calculator is going to come in handy. We're going to do 1.11, that yx button, to the 25. Leave it there. It times 150. And we get y equals 2037. And we're going to stop there. We're not going to round it up because you can't have parts over roundings.